Sorting. So I think you know what sorting is, right? It's where you arrange things into order, right? What's order? Well, I mean, I think we have a sense of ordering of things. Like if I give you a list of numbers, a vector of integers, you have a sense of like sort them from smallest to largest. That's fine. I would say that integers have a natural ordering. They have an order we expect them to be in. Other types besides integers also have natural orderings, like doubles, same thing, order by numerical order. Strings, you could imagine having a natural ordering of alphabetical order. But then you raise questions like, well, is case sensitivity important or not? What about foreign characters, accented characters, things like that? Do we include those? Whatever, right? So some natural orderings are more natural than others. But we generally have a notion of arranging things into some kind of order. By the way, that girl who just signed in and left, I'm totally going to make you sign in twice if you want the points, so fuck her. Just kidding. I love her, but she's not getting the points, though. Anyway, so sorting things into their natural ordering. The interesting thing about sorting is that there's like about 100 different ways to sort that are correct, that work. And some of them have benefits over the others. Some of them are faster. Some of them use more or less memory than others, etc. But there is no one best sorting algorithm. And it's just, sorting is a really interesting problem to study. We're not going to spend a lot of time on it here in this class. But we're going to do a little on it just so you can see it. I think it illustrates some interesting things. It's a good example of using recursion if you do certain sorting algorithms. And also it brings back up some of the stuff we've talked about a little about big O, this kind of thing. So here are some sorting algorithms that people have learned about or talked about in the past. My favorite sorting algorithm of all is called bogus sort. Bogus sort is where, I'll talk about it more in a second, but basically you just randomly shuffle the elements and hope that they got sorted. It's great. I love it. I think some of my 106A students have that approach to solving homework assignments, actually. Boy, I'm just ripping everybody a new one today. I'm kind of salty today. I don't know what it is. Maybe I need more sleep. Sorry. There's also an algorithm we're going to talk about in more detail called selection sort, where you look for the smallest ones and move them to the front repeatedly, things like this. Some of the ones lower on this list are more fancy and actually a little faster, some of them implemented using recursion. All of the algorithms in the first clump here, before the gap here, I would say are what I would call general purpose sorting algorithms. You can use them to sort pretty much any kind of data that can be compared. There are a few algorithms that we won't really talk about today. You could get into them in a later course, maybe if you continue in CS, that are more specialized sorting algorithms. Like if you know you're sorting ints, maybe you can optimize for that a little bit. If you know you're sorting ints in a specific range, numbers from 1 to 1,000, maybe you can use that to help your algorithm go faster. But those algorithms rely on certain assumptions of that nature in order to work properly. Let's talk about my favorite one, bogus sort. Here's the algorithm. Look at the list, like loop over the list and see if it's sorted or not. Like, so any of these algorithms, we're going to assume that you have to be able to tell whether it's sorted or not. Maybe you loop across it, look at the neighbors and see if the neighbors are out of order. If none of the neighbors are out of order, maybe the whole thing is in order. So something like that. You loop across the list and see if it's sorted. If it is, hooray, we're done. Otherwise, if it's not sorted, shuffle them all up into a random order and then try again and see if they're sorted or not. And just keep doing that until the list is sorted. So it raises an interesting question. How long does it take? Now, I know you can sort of imagine that that is going to be slow. It has poor performance, right? But can we be more specific? It's a probability problem, really. So it kind of depends whether you've learned anything about that sort of a probability calculation. It's almost like if you took a deck of cards and threw them up in the air and then let them land on the floor. What are the odds it would land up perfectly? Ace, king, queen, jack, 10, 9, 8, 7. Like, what are the odds of that happening? How would you calculate such a thing, do you know? What would you do, yeah?
So I think there is, assuming there's only one unique ordering that's correct, there are no ties, then I think there are n factorial possibilities.
Yeah.
And one of them is correct. So any given time that you shuffle, you have a 1 in n factorial chance of getting the right answer. And
Yeah.
that is an exponential, but you won't necessarily get to it by the n factorial of time. I think that's a, oh shoot.
No, you're totally, everything you say is totally correct. Yes, if you didn't hear him, what he said was that it's something to do with the factorial. My intuition for it is if you have 52 cards and you flip them up in the air and they land and you hope that they landed in the right order, maybe there's one and only one right order, what are the odds that the first card is the right first card? Well, it could have been any of the 52 cards, so the odds that that one's on top is 1 out of 52. And the odds that the second one is on top, well, is in the second spot, is sort of 1 of the remaining 51. And the odds of those both happening are 1 in 52 times 1 in 51. And the odds of the third one are 1 in 50, and then it's the product of all of those things. 1 over the product of all those things is the product that they all ended up in the right place. So that's the likelihood that we got a perfect arrangement when we threw the cards up into the air. And as you say, so it seems like the runtime is sort of n factorial-ish, and that's pretty much right. The only issue, of course, is that you're assuming an average case where hopefully eventually we'll get the right answer. But it is possible that you never produce the right answer, because that's how randomness works, right? So maybe we'll never get there. I guess what I would say is the average runtime of this algorithm is n factorial, and the worst case runtime is infinite. I love it. And I hope you understand, n factorial runtime really sucks. You don't want that. Because even if n is like 20 things, 20 factorial is a lot. So, I mean, you don't want this as your runtime. So it's just a sort of a stupid sorting algorithm that we would never actually do. So, of course, I wrote it. Here it is. Do you want me to run it? I could run it. I have a program. I wasn't going to run it, but you guys seem like this is up your alley. So I'm going to grab this, BOGO sort. I've got a file here called sorting.cpp. So we're going to write a little bit of sorting code here today. So I'm going to paste this in, BOGO sort. It uses shuffle on a vector. I think there's a shuffle.h I need to include if I want that. I think that'll work now. And then, yeah, and isSorted is something that I have written already here in a support file that we're going to use today. So isSorted isn't very complicated. Just loop over them all. If the neighbors are out of order, return false. If none of the neighbors are out of order, return true. That's not super hard. So there's BOGO sort. So what I'll do is I have like a main here. And what the main will do is I will declare vectors of different sizes. Let's start at size 2 and go up to size 100. And each time we'll double the size of the vector. And what we'll do is we'll make, this is a utility function I've brought in, make up a vector full of random numbers of that size. And then start a timer, and then run BOGO sort on that vector, and then stop the timer, see how long that it took. And then we just print out, for this n, it took us this amount of time. OK, let's do it. Hope you guys are have some spare time here. Uh-oh. Uh-oh. Wait. It's working, but it's so bad. Instead of n times 2, I'm going to do n++ real quick. I think that would be better. So let's try it. Uh-oh. So you might say, why did it go down going from n equals 8 to n equals 9? That's randomness for you. It happened to get the right one faster. I bet if I ran it again, it would do something different. It's just, if you sat here and waited, you would just notice that probably the 11th one takes about 11 times as long as the 10th one. That probably takes about a minute or something, or maybe more. This is horrible. To sort 10 things, it takes it, 5-10 seconds. That's horrendous, right? So, I mean, of course, we're not going to stop here. That's not the algorithm of choice. OK, let's move on to something better then. No BOGO sort. Oh, by the way, there's another sort. Maybe this one's a little bit more subtle. It's called quantum sort. The idea is it relies on all the fact that there's all these parallel universes out there. So the idea is in one of those universes, the data must be sorted already, probably. So if the data isn't sorted, destroy the universe. And the only universes that will be left are ones in which the data is sorted. So therefore, those ones will continue. It's clever. Constant time takes to do that, assuming you can blow up all of the universe in a constant amount of time. OK, anyway, BOGO sort sucks. So let's move on to one that is actually a reasonable algorithm. Selection sort is its name. Selection sort, here's the idea. I mean, this might be something, if I just asked you guys to think about, hey, how would you sort things? How would you describe sorting to a computer? You might come up with something kind of like this. What you do is you sweep across the whole array, find the smallest one, and move it to the front. Sweep across the whole array, find the second smallest one, move it to the second spot, and so on. Sweep across, sweep across, sweep across, sweep across. And it actually works, and it's not nearly as slow as BOGO sort. Here is a picture. So it's an array. I don't know why some of the columns don't have lines on them. It's just a projector thing, I think. So here's an array of integers, or vector, or something. After the first pass, you're basically finding the very smallest value, move it to the front. I think in this case, that's the -4. And I want to be really clear what I mean. When you move something to the front, it's not like array list where you pull it out and you shift everybody over, because shifting is expensive. I just want to like swap it to the front. That's faster than shifting and sliding a bunch of elements over. So what I do after the first pass is I swap the -4 to the front, replace the 22 with the -4. Then I make another pass across, but I'm looking for the second smallest thing and move it to index number 1. I think the next smallest one is 2 from index 12, I think. So that moves to the front. I do another sweep. Is 7 the next smallest one from here? Then it ends up, yeah, the 7 ends up in the third spot, and so on. Does that make sense? OK, I want to code it with you. I bet we can do this, right? I want to code selection sort. And it's right. Oh, no, somebody already coded it. Who did that? No, go away. There. Nobody coded it anymore. OK. Selection sort. Sweep across the array multiple times. The idea is each sweep, we're trying to decide what to put in index I. So we're going to have some sort of int I loop. It goes from 0 to v size. So again, the purpose of the body here is find the right element to go at index I. So if you look at the picture here, look what goes inside my for loop. So like the loop, the outer for loop int I is going to find what needs to go here and then put it here. And then when I do I++ to make I become 1, now I'm going to do another loop to decide what goes in index 1. So what do I do here? Yes?
We're going to loop through all of the elements and store whatever the smallest one is you found so far.
Yeah, loop through everything forward from here and look for the smallest one. So let's make another loop. Int j equals, not 0, but let's start at like maybe I. Because like if we're on the third pass or the fourth pass, then all the stuff before me is already in place. So I don't want to start at 0. I want to start here and loop to the end, kind of. So start at I, and then j less than size also, and then j++. And so right, find the right element to go at index I, which is the smallest one. So maybe what I'll do, we know how to find the smallest element in an array, right? So I think what I'll do is I'll save the index of the smallest element, the min index, equals, let's assume that it's at I at first, and maybe then I'll go I+1 to the end. If I see something smaller than that, I'll remember that as the minimum index. So if the vector at index j is smaller than the vector at index min index, then I will say min index equals j, right? At the end of this loop, min index stores the smallest thing at position I or above. So swap from min index to I. That's what I want to swap, right? And you know how to swap. You just make it temporary and stuff. I've written a little function we can use called swap that takes a vector and 2 indexes, swap I with min index. Just because we're going to be swapping a lot today, I just didn't want to write that code over and over. All swap does is int temp equals I, I equals j, j equals, right? That's not very hard. You know how to swap things. OK, so swap to min index. And then I think that's it. Just keep doing that. So let's try it. Oh, wait, my main isn't calling selection sort. My main is calling BOGO sort. Let's not run that ever again. Selection sort, I'm going to turn up the size a little bit. Let's do maybe more like 1,000,000 elements. And let's start at 10. OK? And let's do, I think the best way to see what's happening is to do n times equals 2. Double the n every time, right? OK, let's run it. By the way, how do we know it works? Well, the main, I'll show you in a second, after we're done sorting, the main does a thing that says if it's not sorted, crash. So it's sorted, otherwise the main would be crashing. So the runtime is happening. We're getting these times coming out. What do you notice about the growth of the runtime? I double n, what happens to runtime? I guess it depends what part of the graph you look at. There's a lot of zeros and little teensy numbers at the top. We kind of ignore them. When we look at these things, we want to look at where the data is a little beefier, where there's a little bit more of a number there. As we get to the bigger parts of the graph, n times 2, runtime times what? It's more like 4. It's not exactly 4, but the longer we would let it go, the more smoothly that would look like a 4x growth. OK, well, why did that happen? Why is doubling n going to make the runtime times 4? If I look at this code, can you answer that question? What does that mean about this algorithm? What's the big O of it, or why is it growing by 4?
It has like an n squared runtime, or close to an n squared runtime.
Yeah, it looks like it's got an n squared runtime. Because, I mean, the way your intuition about big O is whatever change I make to n, what's the corresponding change in the runtime? If I change the n by 2, the runtime changed by the square of 2, which is 4, right? So that means it's proportional to the square of the input size. The change will be squared the change of the input size was. So yeah, that's what's happening. Now, if you look at this code, does that match? If I hadn't run it, would you have been able to tell me that it was big O of n squared? I mean, the whole point of big O, I mean, it's great to run and get these graphs and stuff, but if we really understand, we maybe don't even need to run the code. We can just look at the code and say, that is going to be big O of n squared. If I hadn't run it, how would you have known it was big O of n squared? What would you say?
You have a for loop nesting with a for loop, and they're looping over essentially n elements.
I have 2 for loops nested inside of each other. So it's not only that, but as you say, they are for loops that are going over n elements. So n elements times n elements, that's what number of computations my code is doing. You're right. It's not quite n things, though, right? The outer loop is definitely n, where I don't see n in here. Well, but it doesn't have to literally be called n. N is the size of the input, v dot size. V dot size is n. Those are the same thing. That's what n means. This loop right here, this inner loop, it isn't doing n things, though, is it? It starts at I plus 1, and then it goes up to size. So that some students get thrown by that. They go, well, maybe it's not n times n anymore, because it's not doing as much inside of the inner loop. How many things is this code doing? How many computations am I going to get here? Any ideas? Well, I guess the way I would say it, if you're a spatial person, n times n is like a square, right? If you think of it spatially. And this thing is more like n times half of n. It's more like at index I, you go I things. So it's like 1, and then 2, and then 3, and then 4, and then 5, as opposed to n, and then n, and then n, and then n. The difference is, instead of being a rectangle, it's sort of a triangle. It's like half of the area of if we had done j starting at 0 to size, if we start at j equals I to size. Basically, the runtime of this is about n squared over 2. But it's still proportional to n squared because constant multiples are not factored in when we do big O. Anyway, look, this is the right intuition. It has 2 loops that are both directly related to the size of the vector like that. Therefore, this is an n squared piece of code. And if you ran it on lots of other computers, you would get similar kind of data. I'm going to copy and paste this because I want to save these numbers to compare against other algorithms that we're going to write. So I'm going to paste these right here. OK? There we go. So does the idea of selection sort make sense? The code that we wrote, do you guys understand that so far? Yeah. And if you ran it, you would sort of see a times 4 kind of. This data is from a different computer, but that's kind of what we see. OK, so it's n squared.